minutes to briefly review what we just learned last week because this session is very important. Uh, in this session, we just learned improper integrals. So last week I also show you actually we have two types of improper integrals. So the first type is just like this one. The domain of integration is one of the limits of the integration is infinite. So just take this as an example that I'd like to calculate the integral about this function, but from a fixed number 1 to a positive infinity. So actually in the past we just learned two limits are limited number. Okay, so this is a type 1. The second type is this one. So even though these two limits are finite, however, if the integrand is this one, then based on this domain, this limit, this range, will cause it become infinite number. So taking this example, when you just set x to be 0, you can find the number will go to positive infinity. So even though these two limits are finite numbers, however, we still encounter such kind of problem that if we want to calculate the integral, we will encounter one of them will reach an infinite number. Okay, so this belongs to the type 2 improper integral. So how can we just deal with such kind of integration? For the type 1, we can easily to set a temporal bound for this integration. Taking this example, even though I ask you to calculate this one, but we will set we just assume the b number is a finite number, so that we can just try to calculate from 0 to b. Based on this, we can calculate the integral under this curve. So that we will have a phase 1 process. The phase 1 process is where we try to calculate the integration from 0 to b, where 0 and b are finite number, so that we can get this form. Then finally, we just push the b value to reach positive infinity, so that through these two phases, we can get the improper integral. So you can also notice that if you want to calculate the improper integral, you can see it's just based on the calculating the limit of this one. So that's why I say actually there are two phases to calculate the improper integrals. Okay, so you can see this is what we define for the improper integrals. So this is type 1. So we can see there are two types, from a to positive infinity or negative infinity to b. Then finally, maybe it will be negative infinity to positive infinity. So you can divide it into two parts. Then each part will belong to subtype 1 and subtype 2. Okay, so since it's just about the calculating the limit, so we should notice that if the limit is finite, then we will say the improper integral just converge. However, if we cannot make it, then we will say that the improper integral is divergent. Okay, so I also show you some example. I will ignore this part. I also show you this example. Then finally, I also show you this example that please just at least you should keep this summarization in your mind. If p is larger than 1, for this one, integral from 1 to positive infinity, 1 over x to the power p will converge. If p is less than 1 or less or equal to 1, then this improper integral will diverge. Okay? And then I also show you the type 2 improper integral, right? So this one will based on it is also talking about how calculate the integral from a to b f of x. However, this form just encountered one problem, that one of the two ends will be discontinuous. So for taking this example, when the function reach x is equal to a, then the number will maybe go to positive infinity or negative infinity. So that means at that point, it will not be a continuous point. So if you want to calculate this one, this improper integral, you also need to set two phases for this calculation. The first one is we still set a temporal c. Here, c is not a, because as I told you, for x is equal to a, the function is not continuous. So we will assume we will set a temporal variable c between a and b. Then we can calculate the integration from c to b f of x first. Now we just try to push c to a plus. That means it is very close to a, but it's not exactly a. Then we just define this as the improper integral for this form. Okay, so of course we have subtype 2. Then if we have c sit between a and b, then we can just use c to be a bridging point and separate it into two parts. And for each part, you still can follow the subtype 1 and subtype 2 to find its result, corresponding result, and then finally sum them together. Okay? And before we go to the end of next lecture, we also talk about how to test for the convergence or divergence. So in this case, actually, they don't expect us to get the final limit value. Instead, we just need to answer if the improper integral will converge or diverge only. So that means actually it may not easy for you to get the final value of the limit. However, you still can answer if the form is divergent or convergent. So based on this, you can see the original curve is e to the power of negative x squared, the white one. But we also, at the same time, we also can find a base function. Y is equal to e to the power of negative x. So this is the green one. So you can see after some certain point, the green line, the green curve is always larger than the white one. So if we can discuss, or if we can find finally if the function, the improper integral for the green one can be convergent, then we can conclude for the white one is also convergent, because you can see almost at we can see at any point, I should say at every point, you always can find the green one is larger than white one. So that's why if we can conclude the green one is convergent, then we can also get the result that for the white one is also convergent. Okay, so this is the first case. And this is about the direct comparison test. So you just need to find one function which is determined. We can determine it is convergent or divergent. Then based on this, we can try to, based on this fact, then conclude or infer that the other one is convergent or divergent. So we also have two rules here. So I also show you an example, even though this one is not easy to calculate it. However, if we can see, we can just have the result that because sine square x is always less than or equal to 1, so we can have this relationship. So then we can conclude this one is convergent, so that this one will also be convergent. Okay, and the second test is limit comparison test. So if these two functions, when we just take its limit value for x is approaching positive infinity, f of s over g of s can be a fixed number L. L is larger than 0 and less than positive infinity means that L is a finite number. It's a finite number. Okay, so if we can have this relationship for f of x and g of x, then actually the improper integral for f of x and improper integral for g of x will have the same property. That means once one of two, if we can make sure one of two is convergent, then the other one will be automatically convergent. So similar for divergence. Okay, so this is what we just learned last time. Okay, so today we will move to the new chapter. So this chapter we will talk about chapter 9 we will talk about 等一下8.78.6跟8.7那个部分就用那个部分是在其他的课程会教啦。8至6是讲的是那个整数，我是顺便讲一下for the section 6 in chapter 8, it will just talk about the integral tables. So if you want to calculate the integral, you can just look up the table. So you can just find your textbook if you have, then you can just go back to the appendix section, 就附录页。There is maybe there are around 180 something formulas. So you can just look at the table and quickly conclude the result. So I will not talk about this part because it's just about that you just use the lookup table to get the results. And about the section 7, we will talk about the numerical integration. Actually, numerical integration is also another course. So I think we cannot just spend 1 hour or 2 hours to explain the details. And especially these two parts is not easily, it's not easy to be shown in the quiz or examination. So that's why I just skip these two sections. 8至6跟8至7，8至6讲的是那个积分表或者是 CAS 就是一个电脑的辅助系统。现在有很多那个它是叫 Maple 的系统。现在很多你现在 也不一定要用这个了哈。你现在几乎用 ChatGPT 它也可以帮你回答哦。但是过去有一些电脑软体可以帮你辅助做微分跟积分，甚至是不定积分的计算。所以在8之6它讲的就是，要么你就用电脑系统，要么你就是用这个积分表来帮你算出这个积分的结果。所以这件事情我们就跳过去，这个考试也不太容易考。那8之7是有关于所谓的数值分析、数值积分。数值积分就是当我们要去算一个积分的定积分，我们都知道定积分是从一个 A 到 B， 它是有限的。那我们要去算它的时候，事实上我们可以透过什么黎曼河，这个概念以前也讲过，我可以切割，然后呢加总，然后最终取极限，对不对？可是如果你要落得这种方式去算的时候呢，电脑辅助系统里面还有一个办法，就是你把它做一些近似的方式。我其实课堂上有讲过，上矩形法跟下矩形法我们都教过。那事实上还有其他的方法，比方说你有没有想过，我们切割成一小段的时候，我们不是取最大，要不然取最小，可不可以用梯形法？梯形把最高跟最低之间连接起来，或两个 end 之间连接起来变梯形，把它加总起来。那课本在8之7有讲一个叫 Simpson method， 就是辛普森法。它的做法是把两个之间呢，两段之间把它接起来之后，利用一个抛物线我这个很快讲一下，但是我等一下涂掉哈。For example, if you want to calculate the integral from A to B, so I can divide it into many pieces, right? So especially if I just focus on this one, if I want to calculate this, so you can see there is a point A, B, and C, right? So since these are 3 different points, can we just try to find y is equal to ax squared plus bx plus c, passing A, B, and C. So that means I try to use this parabola to mimic the curve. So you can see the true value is here. But if you just use the parabola, the curve will be like this one. So you can see there are still some gap in between, right? But in this case, you can see for each part, for every 2 subsegments, for these 2 ones, I can find another y is equal to a prime x squared plus b prime x plus c to simulate the curve. Then finally, I just sum them together. I just integral, then sum them together. Blah, blah, blah. So if you can do that, you can just write your program to simulate the integration for the definite integral. 你就可以利用这种方式啊，每2块当做一个 pair， 然后去模拟这个曲线在这里是那个绿色的，那个绿色，因为它只是在2次方而已，所以它在计算上来讲就是比 doable， 是可以做的那这个就是 Simpson 的方法。所以如果我这样很快讲过这个方法，其实大概你们也学过了好几个方法了，就上矩形、下矩形，还有这种方法那你也知道，切割的越详细，计算量越大，但是就越接近真实的结果所以这个，因为这2个都不容易在考试里面去呈现所以我们这2个就跳过去。而且这学期有很多需要讲的，还不只是这些所以我这部分就跳过去
这类似黎曼河的。
对，类似黎曼河的概念，但是它只是每两段之间用一个抛物线的方式去近似它，因为我们知道抛物线只是2次嘛，所以要算积分其实很容易算，因为它的反导函数就是3次OK。 just like a differential equation. Actually, in our textbook, we suppose I also need to introduce this part to you for the differential equations. But you know, for the whole knowledge about uh, differential equation, it will have another textbook. So it is not that easy for us just learn it within 1 hour. So that's why I also skip this part, and because you can just learn the full knowledge for your second year, in your second year. Okay, so then I will move to chapter 9. But chapter 9 we will just introduce the one section only. In chapter 9 we will talk about the infinite sequences and series. So actually, if we talk about the sequence, I believe 对对对，就是不，我是说，就像微分方程，我们在微积分里面照道理应该讲一个段落。以前有时间的时候，我会讲一小段落，但是现在因为时间的关系啊，所以我们就没有讲，没有讲没关系，因为大二的时候工程数学就会讲到微分方程。Okay, so when we just talk about sequences. I believe you may also know that sequence is about a set of number, right? A1, A2, and to AN. So in total, we have n terms. We have n terms. But this is for finite sequence. Just like in our class, in total, we have around 70 students. So we always can give the student one number. Then that may be your school ID, right? Just like your school ID, you are number 1, he is number 2, he is number 3. Sequentially, we can just count how many students in our class, right? But when we talk about infinite sequences, so that means actually we still have some other terms. And finally, actually, we should have infinite number of elements or terms. So finally, actually, we have infinite terms for the sequence. So this is called infinite sequences. Then what is infinite? What is infinite series? The series, I believe you also know that for the finite sequence, of course, we have finite series. So for example, I want to ask you to calculate the sum from turn 1 to turn 2, from turn 1 to turn n. So for example, I ask you to calculate this one. Right? So that means if I want to sum up the values of A1 to AN, then we can use sigma. K is from 1 to n AK. However, if we encounter infinite sequences, then it will become sigma. K is from 1 to infinite, positive infinity AK. Okay, so in chapter 9, we will talking about these ones. Of course, there are some problems or some properties we need to discuss, because for the infinite sequences or infinite series, we always need to check if the sequence is convergent or divergent, because you can see it is just discussing the infinite number of turns. So not just sequences, series also have the same problem. So we need to discuss that, and there are many rules to check it out. However, we don't have time to introduce this part to you because we just have some discussion with some other professors because maybe only some other mathematical tools will be used in your advanced courses. So we will skip this part. 这部分的情况下，我也是很快跟大家讲一下，但是我们这个会讲一个，就是泰勒展开式，等下就会讲这一部分。但是呢，我觉得还是要带一下，让大家知道一下，就是说第9章它讲的是一个无穷数列跟无穷级数。哦，那数列跟级数以前有学过嘛，对不对？有吗？对不对？但是它是有限个的，对不对？有限个的。那现在如果变成无穷多个的时候，其实它就变得很稍微有点复杂哦。无穷多个的时候呢，它甚至就是有些性质啊，不像我们从有限个的去想。好，我讲一个很简单的例子就好了。有限个的时候，假如我们这班有70个学生，我们左边都是奇数号的，右边都是偶数号的，我们把它随便乱 shuffle 加总起来，你考的分数加总起来会有不一样吗？假如每个人都有考一个成绩的话，对不对？不会不一样，因为这70个就这么多个人，加总起来不会改变。但是当你遇到无穷级数、无穷数列的时候啊，它就有一些性质，必须检查到有的情况之下，你这样随便乱调，它才会是同样的值。哦，我打个比方，数列里面都会有个图标嘛，1号、2号、3号、4号，那它可能会无穷多个。一种方法是我从1号加2号加3号加4号加5号，这是一种加法，对不对？另外一种做法是什么？我先把奇数的先加一加，我再加偶数的，这在有些条件下加起来会不一样。啊，你很难想象从从有限的角度去看，因为有限的，你先从1号、3号、5号、7号加，再加2号、4号、6号、8号去加，其实会一模一样。或者你1，然后就跳5、跳9，好，反正 however 你就这么多了。但无穷的时候就把它切成2个无穷的时候，那你加起来可能会有不同的结果。但是这里面呢，在第9章有就会讨论，我就没有时间讨论哈。第9章其实是很快把它带过去，但是我们讲那个98，但是我只是利用这个跟大家复习一下这个数列跟级数的概念哈。Okay, then I would directly go to actually suppose it should be section 8. Wait. Okay. So section 8, we will talk about the section 8, we will talk about the Taylor series and Maclaurin. So see, actually they are also series, but we just named it as Taylor series and Maclaurin series. But before that, we also need to learn one thing. We also need to learn one thing, that what is the power series. So I need to define the power series. And its coefficient. And its center. So the power series a power series is just about x is equal to 0 is a series of the form with sigma n is from 0 to positive infinity Cn x to the power n. So you can see, actually, if we just expand the expression, then we can get C0 plus C1x plus C2x squared plus Cn x to the power n plus blah blah blah. So you can see each term will with the form of x to some power. So that means you can see, if we just start here, you can regard it as a polynomial with degree n, right? If we just stop here, then we will say this is a polynomial. P means polynomial n x. Then we just stop at s to the power of n. That means the maximum power for this polynomial is n. Okay? So once we just we can also try to expand n is approaching positive infinity, right? Then if we say a power series about s equal to c, then it is a series of the form of sigma n is still from 0 to n Cn x minus c to n. Then so you can still understand that actually this will be C0 plus C1 s minus c. Oh, sorry. Normally we say a. Okay. In our textbook we use a. C minus a plus C2 s minus a squared plus blah 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 blah. Here Cn x minus a to the power n plus blah 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 blah. So this is a power series about s is equal to a. So you can notice that the difference between here to here is, in general, we will have c s as 0. Sorry, a special case is s is equal to 0. But the normal case is s is equal to a. So that means a could be 2, 10, 5, whatever positive number. Okay? So this is actually this part is defined in section 7. But I just moved because I want to introduce Taylor series or Maclaurin series to you, so I need to give you the background knowledge about the power series. 这一段事实上是9至7做，你回去翻教科书的时候，它是9至7就讲。但因为我们重点是9至8，所以我把9至7的东西带到这边，只要整合起来哈。因为你如果想要看仔细一点，请自己回去翻9至7的内容哈。And why we should learn this one? I will give you an example. That, for example, sigma n is equal to 0 from 0 to positive infinity x to the power of n. It will be this one. Actually, this is a geometric series with ratio x, and it will converge if taking as the value of x less than 1, that means when s is from -1 to +1, it will converge to 1 over 1 minus x. So I just want to use this simple example to show why should we have the power series, or later on we will learn about the Taylor series. Why should we have that? So you can see this one, that so this one is f of x, but we also have p and x. Did you remember what is p and x? P and x means I just take n plus 1 turns. That means the maximum power is n. So in this case, p and x will be 1 plus x squared plus tier s to the power n. So I just want to ask you to look at these two functions. So if I ask you to draw P0x, what is P0x? P0x of x should be 1, right? What is P1x? 1 plus x. What is P2x? 1 plus x squared, right? So let's just look at these several functions. P0x is 1. P1 of x should be 1 plus x. Then P2 of x is equal to 1 plus x squared. Right? So you can just try to draw it. P01x, it will be x, y. This is 1. So this is P0x. Then we try to draw P1x. P1x, it will be a slanted curve. This is P1x. Then what is P2x? P2x will be a parabola. So it will be something like this. So as we include more terms, then finally we still have several, right? Then finally it will approaching to this one. This is f of s is equal to 1 over 1 minus x. So we still have many, right? P1, P2, P3, many functions. But as we consider more terms for P and x, you will find the curve will keep closer to this function. You understand that? It's just like an approximation. So in the past, we already learned the concept. What concept we just learned? Linearization. Did you remember linearization? Linearization will just stop here. It will be 1 plus x. It will be a linear function. But right now we can consider more terms with a higher degree, higher power. If we consider more, then the polynomial function will be getting closer to this function. So in the past, maybe we just stop here. We just consider 2 terms, but right now we can consider more terms with s to the some certain power. Okay, so this is example why we need to do that. Of course, for this part, it's also not that easy as I mentioned to you, but in this chapter, what I expect you to learn is just how to get the Taylor series. So then we will formally to talk about the Taylor series. So that means if I give you f of x, then I hope you can just expand it as sigma n is from 0 to positive infinity an s minus a n, right? So you can take a look at here. Here is our target, right? And here is our approximation. So I hope sorry. Okay. So I hope if I can give you this one, can you find this approximation just like this one? So that if I can find this one, you can just calculate its value, approximated value. Then by consider more terms. Okay, so this is the basic idea. 我们快跟大家解释一下，好，大家可以看得出这个图形的效果，对不对？它原来的图形应该是这个样子，但是我有一个近似的，怎么来？等一下就是要请大家去学习怎么去取得这个哦。但是这个目的是什么呢？因为过去呢，比方说我可能给你这个图形，不一定是长这个样子啊。好，比方说大家有没有想过sin跟 cos 的图形怎么出来的？哦，其实也可以用泰勒展开式来做啊，也可以用这种展开式来做。那你看，我先告诉你答案嘛，哈，就是说这个呢，事实上是可以用这个来近似出来的。那我就画了图给大家看。等一下我们讲怎么做出这个了哈。我们先稍安勿躁，我们先看这个 Pn of x 呢，你看它每一项都是什么的幂次组成的，是一个多项式的组合，对不对？那的好处是什么？每次你要算它的时候，其实你只要再多考虑一项，就越来越近似它。右边的图可以看到，一开始如果你只考虑它的第一项而已的时候呢，事实上它非常跟原来的这红色的线是非常的不像。但是考虑第一项进来的时候，它已经开始有斜线的效果出来了，对不对？随着接下来考虑3项的时候，它就会有抛物线的效果出来了。也就是说，你考虑的越多，它就会越来越近似这条线，这条曲线。甚至考虑到它有无穷项的时候，基本上它就是跟这个是贴在一起的哦，它就跟这个贴在一起了。好，那现在就回到一个问题：如果我给你这 f of x， 我们是不是要想办法找出它的长相会是什么样的这样的一个形式？那这里面包含什么呢？我会告诉你这个 f of x， 我会告诉你的展开中心 a， 这 a 不一定是0哦。那我希望你找出这个 an， 这里这个很 lucky 哈，这里全部都是1，我发现都是1，可是不是每个人都是这样子哦。所以我们的目标呢是要把这个展开出来哦。So our purpose is if this f of x could be this one, then that means it will be a0, a1, x minus a, a2, x minus a square, blah blah blah. Then an, x minus a n plus blah blah blah. So how can we just get a0, a1, a2 till an? So this we call it coefficient. This coefficient, how can we get that? Then later on, after the break, I will show you how to get it. Okay? 好，我们休息一下哈。Our target is, can we just convert fs to be an infinite series like this one? Then what we need to do is we need to determine these coefficients from a0, a1 to an, blah 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 blah. Okay, so how can we do? So if we want to meet this requirement, then we can try to differentiate. Of course, we assume the function is differentiable. We assume this f is differentiable, so that you can see it will be a1 plus 2a2 s minus a. You can make it smaller. You can just have a comparison. Then 3 a3 square n s minus a to the power m plus blah 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 blah, right? Then we can continue to differentiate. Since this is a constant, so we just continue to differentiate it. This part will vanish. Then we will have 2a. 1, 2, a2 plus 2 times 3, a3 tier n minus 1 times n right? So we can continue to do that. Tier differentiate n times. Yeah, we can get this one, a sum of terms with s minus a as a factor. So this general form is very important. Okay, so you can just check it out. Let me just make sure one thing that so here we will encounter n factorial. n 阶层 switching on. Okay. N factorial means n times factorial n minus 1, n minus 2, t 1. Okay? So because, you just continue to differentiate, the power will be moved to the coefficient. So finally, it will become this one, n factorial. Then we also have a sum of terms with x minus a as a factor. So you can notice this part is n factorial an, right? For the rest part, they always have s minus a as its factor. So if we just differentiate f of s n times and using a as an input, and you can see we can just get n factorial an plus 0. Why? Because all terms, for the rest terms, they always have x minus a as its factor. So when you just use a as an input for this one, starting from the second term will become 0. We will have this term that n factorial times an. So that based on this, we can get an is equal to nth derivative of a over n factorial. So this is what we want to get. So did you remember our purpose is to get the a0, a1, an, blah blah blah, an and an plus 1, an plus 2, right? So right now we can conclude an should be this one. N should be this one. N's derivative of a over n squared. If we can get this one, then we can get f of x is equal to f of a plus here, right? F from a times s minus a plus f double prime a 2 factorial s minus a squared plus blah 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 here f the nth derivative of a times divided by n factorial times x minus a to the power n. So this is very important because we already can get the coefficient, we can just put the coefficient e. So once we can get it, I will give you what is the Taylor series and what is the Maclaurin series. So let f of x be a function with derivatives of all order. So n here is the order, right? This is the first derivative. This is the second derivative. Then this is the order n derivative, right? So we assume f can be differentiated as in any order, then throughout some interval containing the center A as an interior point. So then we will say the Taylor series generated by this f of x at s equal to a is sigma from k from 0 to infinity, order k derivative of a k factorial s minus a to the power of k. Let's remember the coefficient is this one. So let me just emphasize that again. You can see here is the AK, right? Maybe sometimes we know it down as AN, sometimes we know it down as AK. It's fine. Actually, this K is fine, N is also fine. Okay? Then that will be f of A plus f prime A s minus A plus f double prime A divided by 2 factorial s minus A to the power of 2. Blah, 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 blah. So this is the Taylor series. And what is the Maclaurin? Actually, Maclaurin is just, the only difference is almost the same by f of s. But this time, we will not have this one. We just simply is sigma. K is from 0 to infinity. The order k derivative of 0 is f of 0 plus f prime of 0 times s minus a plus f double prime of 0 divided by 2 factorial s minus a square. Then sorry, right now we don't have a, right? We don't have a here. We just only x left. Because this time we don't have 0. We don't have a because s minus 0 is equal to x. So this is a Maclaurin. So when someone asks you, can you just have the Taylor series for some function? Normally, he will give you two important parameters. The first one is this one, and the second one is what is a. But if for Maclaurin, you just focus on f of s, but actually a here is equal to 0. So we will not say that. We will not specially point out that a is equal to 0. If I just simply say, can you just get the Maclaurin series for some function, that means it just gives you a hidden message that s is equal to a. 所以 泰勒展开式或者 Maclaurin series 呢，两个差别实际上是差别在一个是在对 A 展开，一个是对0展开。所以如果在问泰勒展开式的时候，通常他会给你两个很重要的，就给你函数是什么 fs。那目标展成这样的时候，你要提出它的展开的重心是在哪里哦？那如果是 Maclaurin 呢，基本上呢就是暗示你那个 A 是0哦。Okay, so I will give you an example. For example, find the Taylor series generated by f of s is equal to 1 over x at a is 2, where does the series converge to 1 over x? Actually, this part is not as sure as I teach you. It's we need to talk about 3 sections that under the whole picture. However, because due to the time constraint, I can just show you how to explain it. Actually, there are some stories we need to tell. The first one is we generate the power series, but actually for power series, it's not always convergent. In some special circumstances, it can be convergent, but sometimes it will also possibly divergent. So actually, at least we need to discuss 3 sections in this chapter, but we don't have time, so I just teach you how to explain it. 这个章节其实是有点多了哈，这个如果严格说起来，要教起来把它完整教完，这个章节起码要耗掉我们3周的时间，2周到3周，但真的是时间的关系，因为后面我们还有那种多变数的微分，还有多变数的积分，还有参数式，这也都非常重要，所以我们只要舍弃这一块。但我很快跟大家讲一下，你回去有空也可以务必的把它看完一次哦。但是第9章这一系列它其实讲的还算很完整，但是我们只能讲这个重点。那这个重点是在于，我很快讲一下，就是说我即便就在 FOS 呢，把它展开成这个哦，刚刚我们讲嘛，我们的希望了哈，我们当然希望说，我给你一个 FOS， 你就可以展开出这个样子，对不对？那这里可不可以画上等号？其实未必哦，但是我期待它做到，我希望它从这里可以展开成这样。所以在这一章的7、8、9，我们现在直接讲8。7呢是告诉你，如果我给你一个，先不要管这个，我会给你一个这个，你可不可以找出它在哪一个区间是收敛的？因为我给你这个东西呢，它也有可能是发散的。我刚刚讲的级数，它有可能是发散的，它应该加到无穷项了，所以它可能是发散的。所以我会给你这一段，但是你去判断在哪一个 x 的范围里面，它会收敛。这是9之7所讲。9之8呢，他就教你说，那你可以用泰勒展开式，我给你一个 FS， 你去展开出来这个样子。如果你展开出来这样子，你就要去检讨它这个的收敛区间范围在哪里。然后呢，它收敛完之后呢，它有没有跟这个是越来越接近的？课本也举个例子，你可以展开，未必跟它会原来长得一模一样，这也是很特殊的，对不对？你展开出来之后，可能在某一定的区间，你才会跟它 很接近。这个是一个它的介绍的顺序是这样我再讲的是97，我告诉你很多这种 power series， 但是呢，你去判断在哪个地方会收敛。98呢，告诉你一个 FOS 之后呢，你想办法找出它的展开的 power series， 但是呢，你可以用9之7的方法去判断它的 convergence 或 divergence 更容易出现。但是在9之9、98、99、99，你还连带要去检查这个有没有越加越多的时候跟 FOS 有越来越接近，不然的话它就不能收敛成这个。不过那我们没有时间谈了所以我们多半后面讲的这些例子都会是展开出来之后，它就会收敛到这个去。但是这个是不必然的这个是需要跟大家稍微解释一下的Okay, so let's just have some practice. That right now I just give you FOS, right? Then I also give you where we want to explain. Then finally, the question just continue to ask, where does the series converge to the 1 over x? So you can see if the problem that asks you where does the series converge to this one, so that means it is not always happen, right? Once you know how to generate the sequence, but the series. However, if the problem that asks you where does the series converge to the original function, that means sometimes the series cannot converge to 1 over x. Okay, so that's why the problem that asks you where, 对不对？这个题目那这样问就代表什么？它不是所有的都会 converge 到这个，虽然你用这个去展开出来，所以这个题目里面也很有意思。从这个题目你就知道它其实不完全是从那个长出来之后呢，就完全收敛到它那边，是要做一些检查的了但我只能带到这里因为有几个负面的例子，我们也没有在这边跟大家讲，但确实有这种事情发生Okay, so let me show you how to get that. So if you want to get this one, solve this one, the original FOS is 1 over x, so that is x to the power of negative 1. So f of 2 will be 1 over 2, right? Because our center is 2, right? So that's why we just use 2 as the input for all of FOS. Then f prime x will be negative s to the power negative 2. So f prime of 2 over 1 factorial is negative 1 over 2 to the power 2. Then we continue to get double prime. Now we can get 2 factorial s to the power of negative 3. Then we can get the coefficient is f double prime of x double prime of 2 over or divided by 2 factorial. Then we can get 1 over 2 to the power 3. So here you can see here is A0, this is A1, this is A2, right? Following the same way, we can continue to get f n order derivative of x will be negative 1 to the power of n factorial s to the power of negative n plus 1. You can check it out. Actually, this is the general form. Once it's 1, and we can get this one. Once E is 2, then we can get this one. 2, we can get this one. Once E is 1, we can get this one. Once E is 0, we can get this one. So in general, it should be this one. And also for the in general one, the f n order derivative 2 over n factorial, and we can get this one is. So finally, this is an. So right now we already collect a0, a1, a2, blah 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 to an. So then we can just put them together. So the Taylor series. So the corresponding Taylor series is f of 2 plus f prime 2 1 over 1 factorial x minus 2 plus f double prime of 2 over 2 factorial times x minus 2 to the power of 2 plus blah 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 here. N order derivative of f of x 2 over n factorial times x minus 2 n to the power of n. So finally, you can see actually it's a little bit complicated. It will be, okay, the first term, let me make it smaller. So the first term is this one, right? 1/2. Then negative 1 over 2 square s minus 2 plus 1 over 2 to the power 3 s minus 2 to the power 2. But here, the negative 1 to the power of n, 1 over 1, 2 to the power n plus 1, then times x minus 2 to the power n. Right? So I just simply put a0, a1, a2, blah, 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 to an to the power series. So the most important process is the first process to get the a0, a1, a2, and an coefficients. Then finally just put them together. Then this is the so-called Taylor series. When a is equal to 2. Then where is it convergent? I'm not sure if you just learned geometric series before. 那个几何级数以前在高中的时候学过吗？几何级数。我们知道数列跟级数有一种就是等差级数，这是最早学的，对不对？等差级数，什么叫等差？1、3、5，级数就全部加总起来哈。1、3、5、7、9，我跟前面的差都是固定2。1、4、7、10，我跟前面的 term 都是差3，这叫等差级数。对，那什么叫等比级数？这一项跟前一项之间，它有呈现一个比值，叫1加1/2加1/4加1/8，前项后项比是1/2。 那这个就等差级数就是所谓的几何级数 （geometric series）。So you can also notice that this term divided by the previous term, you can see a common factor. This term divided by this one, you can see it will be 1 over 2 times x minus 2. If you just use this term divided by this term, you can see it is also 1 over 2 times x minus 2. So you can always see that when we use this one divided by this one, or we use this one divided by this one, we always can get its R is negative 1/2 times x minus 2. And its initial value is 1/2. So in this case, it will just converge absolutely if R absolute value is less than 1. So that means absolute value of 1/2 times x minus 2 should be less than 1. Then it will converge to A divided by 1 minus R. 几何级数呢？这个就前面没有讲的很详细，如果大家忘了高中所学几何级数，可能就会忘了这一块哈。没关系，这个考试的时候我们可能会考到展开就好了哈。但是这边我很想跟大家还是要讲一下，就是说几何级数它如果要收敛的话呢，它必须收敛在你的比呢绝对值要小于1，前项比后项的值要小于1的情况之下，你才会收敛。那至于它收敛到哪里呢？会收敛到这个首项去除以1减到 r。But no worries. In our midterm exam, we will not include this one. I just hope you can learn how to explain it and then get the Taylor series. So maybe we will not ask you to think about where is the x range to make the series to make the series convergent. So this part will not be included in the midterm exam. However, I still hope you can learn this part also. Okay, so this is the first term, and this is the ratio. So based on the property of a geometric series, then it will converge to A over 1 minus R, so that we can continue to do that. For this part, x range will be s minus 2, taking absolute value is less than 2. Then we can get s minus 2 is larger than negative 2 and less than 2, so that we can get x is larger than 0 but less than 4. Okay, then if we want to know what's the convergent number, then it will be A is 1/2, then R is negative 1/2 s minus 2. So we can see it will be 1/2 over 1 plus 1/2 x, then minus 1. So you can see finally this part cancelled and this part cancelled, then finally it's still 1 over x. So let me just conclude it. If x is located between larger than 0 and less than 4, then the series will converge to 1 over x. Let me show you again. If x is in this range, I can make sure your series, you just expand it by the Taylor series, then the series will converge to 1 over x. 这它的展开是展开出来，你看展开出来之后，还不是所有的 x 都会收敛到这里哦，它只有在什么时候？在 x 介于0到4之间的时候呢，你这展开出来的式子啊，会收敛到1减掉 x。所以我们再回过来，这个题目是什么？本来我给你1减掉 x， 我期待你去展开出来长这个样子。那展开的中心点是2。所以呢，经过这样的分析下来，你会发现，只有 x 在介于0到4之间的时候，它的这个展开出来的展开式，这个展开式才会收敛到原来的生成它的函数上面去。这个1 over x， 所以这是一个很重要的观念啊。可惜我们这一次没有办法在这里面很详细讲这一块哈。Okay, and then I will show you the second example. This is the first example. Then the second example is find Taylor polynomial for cosine x at s is equal to 0. Okay, so right now I already give you the function and also give you the a. A here is 0. So actually find Taylor polynomial. This part is also try to find the Maclaurin, right? And the so-called Taylor series vs Taylor series. The only difference is Taylor series, we will have infinite number of terms. But for the Taylor polynomial, we just consider n terms. For Taylor polynomial with n means we just consider a0, a1 times x minus a, a2 times x minus a squared, here an times x minus a to the power n. We just stop at the n plus 1 term. But for Taylor series, no, we will continue. In the finally, we will have infinite number of terms. 这两个差别是 Taylor polynomial 是只有考虑 n 项而已，但是如果是 Taylor series 考虑的是无穷项这两个差别，刚刚我提到。I just point out the idea here. This is a Taylor polynomial and stop at n. This is power series. This is the Taylor series. Taylor series, we will have an infinite number of terms. But for the Taylor polynomial, we just stop here. The maximum term is the term with power as n. Okay. So if I want to ask you to do that, then you can start to calculate. The first order is cosine x. The second order is negative sine x. The first order is negative sine x. The second order is negative cosine x. Then f triple prime x is sine x. Then you can see it will loop, right? It will cosine x back, right? You can see here and here. It will start the loop, right? So when we just want to get this and explain it when x is equal to 0, then through this, I just skip some calculation, but the final result will f the order 2k 2n of x will be negative n to the power cosine x. Then f the m plus 1 order of x will be negative 1 to the power of n plus 1 sine x. Because you can see 4 and 5 will go this turn, 6 will go this turn, 7 will go this turn. So always loop, right? So finally, we can conclude actually they have the property like the right hand side shows that it's just show the loop for this one. Then when we just explained it at s is equal to 0, so f the 2n order of 0 will be negative 1 to the power n, and f to the power 2 the 2n plus 1 order of 0, since it will be sine 0, right? Sine 0 always 0, so this term will always 0. So this term will be always 0. So its corresponding Taylor series will be f of 0 plus f prime 0 x f double prime x squared divided by 2 factorial. Then it will be 1 plus 0x plus negative x squared over 2 factorial plus 0 s to the power 3 plus s4 to the power 4 divided by 4 factorial. So finally, the result will be sigma k is from 0 to infinity negative 1k times x to the power 2k divided by 2k squared factorial. So we can conclude that p2n of x is equal to p2n plus 1 x. Why we say p2n x will be p2n plus 1? Because you can notice that this is the first one, p0. Then p1 will be 1 plus 0. Did you notice that? Give me 3 minutes. This is p0. Then this one is p1, right? This is p2. Then this one is p3. So did you notice that p0 will be equal to p1? Why? Because we just add additional term, which is 0. So p0 will be p1. p2 is here. then P3 with an additional 0. So that means P2 will also become, they are the same. P2 and P3 will be the same. So similarly, P5 is equal to P6. So finally, we can conclude this one. Okay, then you also can take a look at the figure. You can also take at the figure. So I also can show you the figure is just like this. This is P0. This is P0, P1. Then this one is P2. P2x is also become to P3. So as we consider more terms, then for example, this is P4 S will be P5x. So you can see, as we consider more terms, it will become more like the shape of cosine x. Cosine x should be just like this one, right? So consider more terms, then the shape will become more closer to the curve of cosine x. Okay? So for this part, I just quickly give you some concept about the Taylor series. But you know, in our examination, we will not include too complex computation. However, I hope you still understand the concept. Even though we just ask you to simply explain the function to get its Taylor series. OK， 就是我们在期中考的时候不会考这么复杂了哈，但是我觉得大家还是要花时间去了解它这个概念。期中考的时候，我们最多就让大家去做一下泰勒展开式，去感受一下泰勒展开式这个动作而已。但是它其实后面有很多相关的观念，其实应该要去结合起来哈。好，那我们今天上到这里哈。